Hello, everyone, and welcome to another wonderful day of chemistry. So far this chapter, we've been evaluating the favorability of a reaction or its spontaneity using the total entropy. But let's just be honest, total entropy is a little bit hard to use. So oftentimes what we're going to try and do is replace it with a more useful function. Because again, so far we've said that we can go ahead and evaluate the spontaneity using the second law of thermodynamics, knowing that the universal entropy has to increase, and we can calculate that universal entropy based on the system and the surrounding. Well, the system is going to be intrinsic to what's happening. We've really evaluated that pretty well. And the surrounding is based on how much heat the surroundings are adding in, because that's the major way I'm either ordering or disordering the surroundings is by either putting energy into it, which is disordering the surroundings, or pulling energy out of it, which will be ordering the surroundings. But using the heat of the surroundings is a little awkward, so we go ahead and replace it with the heat of the system. With the idea, the more heat the system releases, the more favorable the reaction because we're again putting that energy into the surroundings, disordering it. Now, part of the issue that we run into here is the heat is a path function. And we really want to go ahead and replace this with a state function. Now, that means that the best way to do this is going to be to constrain the system. If I constrain the path of the heat, I get to replace it with a state function. So what state function can I use? Well, the simplest one is going to be assuming an isochoric case. Because if I'm using an isochoric case, then I can replace the heat with the internal energy, which will be based on the isochoric heat. So at this point, if everything is isochoric, then congratulations, I can calculate the isochoric entropy of the universe based on the entropy of the system and the change in internal energy. Again, as long as it's isothermal, this is a really easy case. So this allows for the spontaneity reaction to be determined just by knowing the internal energy and the system entropy. The problem is that, again, we run this issue that now we've got two different kinds of entropy, which will be hard to keep straight. And let's just be honest, entropy has a little bit of odd units. We don't necessarily want to use joules per mole Kelvin. So one of the ways we can simplify this is by multiplying both sides by a negative t, which will go ahead and give this left-hand side units of joules per mole. So again, now we're in units of energy. And by changing the sign, that means we also apply to the conventions of energy. Lower energy is better. Negative energies will be favorable. Now, when we do this, we generate a new state function called Helmholtz. So this change in A is going to be the change in the Helmholtz free energy. And so this is going to be, again, a measure of favorability, and it can be calculated based on the change in internal energy and the change in entropy in an isothermal case. Now, this brings us to a question of what the heck does the Helmholtz free energy mean? Does it have any physical meaning besides just the idea of favorability, with a negative free energy being favorable and a positive being unfavorable? Because it's just going to be sign flipped from our entropy. Now, to do this, we're going to go ahead and go to this definition, and we can go ahead and insert what we know about the internal energy. So we know from the first law, the internal energy is just going to be the heat plus the work. But the nice part here is that lets me choose any single path I want. Well, it turns out the path we know the best is the reversible path. And if we remember, the reversible work is the maximum amount of work I can get out of a system or the minimum work it takes to accomplish an action. But that also gets me the reversible heat. Now, reversible heat actually turns out to be pretty useful because that's related to entropy. Because what we can do is then inserting this definition for internal energy, we get the idea that the Helmholtz is going to be related to the maximum work a system can accomplish, the reversible heat minus T delta S. But remember, delta S is just going to be reversible heat over T, which means the reversible heat is just T delta S. So we can insert that definition for the reversible heat. And when we do this, we get really lucky because these two terms promptly cancel out. And what we're left with is the Helmholtz free energy is just the maximum work a system can accomplish, which means if I have a favorable or negative process, this is the maximum work I can extract out of a system. And if it's positive, it's the minimum work I need to accomplish a process. To make a spontaneous, a unfavorable thing suddenly reversible or spontaneous. It's also the max amount of work I can pull out of a system before it becomes non-spontaneous. And this is where those units of energy get really lucky. It tells me maximum energy out or minimum energy in. Where again, we can really evaluate this based on how favorable reaction is based on that change in energy of a system. Because again, remember, if a reaction is naturally favorable, I'd have a negative change in the energy. And then again, we can cancel out how much energy I gain from random motion. Once I correct for those things, this will tell me how much more of the energy is extractable. So we really need to do the difference of this to get the organized or usable heat. So again, this is actually a fairly useful number. And as a consequence, Helmholtz free energy is very commonly used by engineers because it tells you the maximum energy you can get out of something. Now let's go ahead and apply this to an actual reactive system. So let's figure out the Helmholtz free energy for something simple, the vaporization of water. Now we're going to do this at two different temperatures to really evaluate this. So again, we can look at, we're going to for now not care about the temperature dependence of the internal energy of vaporization or the entropy of vaporization. Let's assume this is relatively constant, which isn't a bad assumption. Now we can go ahead and look at both these numbers in tables, and we can figure out how favorable the system is at 25 degrees C. So if I do this, I'll go ahead and put in my internal energy and my entropy, and then again, at 25 degrees C, this is going to be 298 Kelvin. So I plug in all these numbers. Notice the units of Kelvin will cancel out. Here you always have to watch out for units because again, the internal energy is in kilojoules, the entropy is in joules, so you do need to unit convert. When you do this, you'll find out the entropy wipes away a lot of that internal energy, and we're left with a Helmholtz free energy of about 9 kilojoules per mole. Notice this is positive. This means I need to put in about 8.5 kilojoules of work in order to make this reaction happen. It's naturally unfavorable, so energy has to enter the system in order for it to happen. Now, let's change that temperature. Now, when I do this, again, our internal energy and our entropy aren't changing. We add in our 273 for 100 degrees, 273 Kelvin for our 100 degrees Celsius. Now, when we do this, we note that this value is now negative. This reaction is favorable. Now, mind you, only very slightly, which makes sense because we know that this process is reversible at 0 degrees, so it should be 0. Now, the reason it isn't is a very interesting thing because the boiling point we use is for isobaric conditions. And we know the internal energy is always a little lower than the enthalpy, which means that this reaction is slightly more favorable and thus a little bit lower energy. This is also proves an important point that you have to pay very close attention to when we're looking at favorability. Are you looking at isochoric or isobaric conditions? But again, note that this temperature dependence will often swing whether a reaction is favorable or unfavorable. With whatever process is dictated by entropy becoming more favorable at high temps. Now, the issue is while engineers may like isochoric conditions, we like isobaric. So next time we're going to do the same trick to evaluate the favorability under isobaric conditions. And doing so, we'll get one of our favorite state functions. Next up, Gibbs free energy. Until then, take care.